Hi. In switching power supplies or any device that uses MOSFET for switching, the important issue is how to turn the MOSFET on and off. Turning on the MOSFET is not that difficult, but turning it off is very important. There are many circuits for this. I will try to check some circuits and explain their work. Well, let's check together. To turn on the MOSFET, we need to charge the gate capacitor of the MOSFET with a voltage higher than the gate threshold voltage. This voltage can be provided by the driver or any part. Consider this MOSFET. This is an N-channel MOSFET. The load or consumer is connected to the drain pin and the source pin is connected to the ground. By default, we can connect a microcontroller to MOSFET with the help of gate resistor. To turn off the MOSFET, we put the gate source resistor. This circuit has many flaws. The current should not be high. When the MOSFET turns on and off, we always have a reverse current from the gate to the driver. If the microcontroller is connected directly, there is a high possibility of burning the microcontroller. This return current may reach the gate through the drain and capacitor CDG and be transferred to the micro. Now, if we have a strong MOSFET and the consumer needs a high current, we must raise the gate source voltage above the threshold so that the MOSFET turns on completely. We know that there is an inverse relationship between RDS on and voltage VGS. So, we have to use a driver to turn on and off the MOSFET. The simplest method is to use a second transistor or MOSFET in the gate path. I use an NPN transistor. The collector pin is connected to the voltage with a resistor. This voltage supplies the gate. We call this resistance R1. The base is connected to the microcontroller with the help of a resistor. We call this resistance R3. The output of the transistor is connected to the gate pin of the MOSFET with a resistor called RG. We call this resistance R2. The load is connected to the drain pin. MOSFET is N-channel. The pulses generated by MCU. PWM pulses have a rising edge and a falling edge. The area called T-on has a voltage and the part called T-off is without voltage or zero. We call this entire section a period called T. When the pulse is on, the NPN transistor turns on. When the transistor turns on, the ground reaches the collector through the emitter and this point becomes 0 volts. If this resistance does not exist, the positive and negative voltage are connected to each other and a short circuit condition is created. So, the existence of this resistance is necessary. There is no voltage in the gate path and the MOSFET is off. In the next half cycle, the pulse is off. So, there is no voltage on the base pin of the NPN transistor and the transistor is off. The connection between ground and collector is broken. The voltage reaches the gate of the MOSFET through the resistor R1 and the resistor RG, and the MOSFET turns on. It looks like a good circuit, but it has many problems. The switching speed in the circuit is low and causes a lot of losses. If we reduce the value of resistance R1 so that more voltage reaches the gate, when the MOSFET is off, the current is connected to the ground through R1 and through the NPN transistor and increases the losses. On the other hand, if the value of R1 is small, it is possible that too much voltage will reach the gate of the MOSFET. This amount should not be high. The value of this voltage is written in the MOSFET datasheet. As the gate voltage increases, the ring state is created. Now, if we increase the value of R1, sufficient voltage will not reach the gate of the MOSFET, and it may again create the ring mode that occurs when the MOSFET turns on. But the circuit is still usable. That is, we can turn on a MOSFET with a small amount of current produced by MCU. Well, this was a simple circuit. There are different circuits to turn on the MOSFET on and off, which are called gate drives. The purpose of all these circuits is to be able to charge and discharge the CGS gate capacitor quickly. It means that we can create a path to charge this capacitor and have a second path to discharge it. In all circuits, there is a resistance on the gate. The duty of this resistance is to control the charge and discharge of the CGS gate capacitor, which also determines the switching time and does not allow high voltage to enter the gate, so the ring is not created. If the value of the gate resistance is low, the CGS gate capacitor will charge quickly and the MOSFET will turn on quickly. If the value of this resistance is high, the capacitor will be charged later and the switching speed will decrease. If the value of this resistance is too low, the drain source voltage will suddenly increase and the ring will be created again, which is the reason for the current changes in relation to the time changes. So, the gate resistance is related to the switch time. Of course, it has other effects. In strong MOSFETs, in order not to create a ring on the gate, they often increase the value of this resistance, which reduces the switching speed. The sponsor of the video is Pictech company. This company is located in Germany and has more than 400 products in the field of electronic measurement for use by students, universities, and schools. Be sure to visit the website and visit Pictech products. Well, back to the video. What is important for us is how to turn off the MOSFET. This diode helps the MOSFET turn off faster. When the MOSFET is turned off, the resistance RG is bypassed by the diode and the negative voltage moves to the driver and turns off the MOSFET. In this circuit, a gate drive is often used for the MOSFET. In this case, the diode helps to reduce the voltage and reduce the shutdown time. The next method is to use a PNP transistor on the gate, which causes the voltage of the CGS capacitor to go to zero. When the MOSFET turns on, the current passes through the diode and the MOSFET turns on. In the next half cycle, the zero voltage reaches the base of the PNP transistor through the resistor RG and the transistor turns on. The gate and source are connected to each other through the PNP transistor, and the capacitor CGS is discharged and the MOSFET is turned off. In this mode, the gate source current exists between the PNP transistor and the MOSFET, and it does not reach other parts, and voltage peaks do not occur. The next method is to use two NPN and PNP transistors. In this circuit, the signal can be sent by any circuits, such as micro or gate drive. A bypass capacitor is often placed between the collectors. There is also a bypass capacitor on the voltage pin of the micro. Because in this case there is a possibility of producing noise, a resistor is placed between the bypass capacitors. The signal reaches the base transistor Q1 and Q2 through the driver, so there is voltage on the base. The NPN transistor turns on when the voltage is applied. The voltage also reaches the base of the PNP transistor. Because the PNP transistor turns off when it receives voltage, then this transistor is off. The voltage enters through the NPN transistor and reaches the gate through the resistance RG, and the MOSFET turns on. This is the current sink. In the next half cycle, zero voltage reaches the base of transistors Q1 and Q2. Zero voltage reaches the base of the NPN transistor, and the transistor turns off. The same voltage reaches the base of transistor Q2, and this transistor turns on. The voltage in the capacitor CGS reaches the emitter of the transistor Q2 through the resistance RG and is connected to the ground through the collector. So, the capacitor CGS is discharged and the MOSFET turns off. Transistor Q1 is a current source and transistor Q2 is current sink. This circuit is suitable, but if the frequency increases, the BJT transistors are not fast enough to turn the MOSFET on and off. We can also use MOSFET instead of BJT transistor. If this topic is interesting to you, write a comment so that we can talk more about this topic in the next videos. Thank you for your time to watch this video.